Yeah, welcome everyone to today's ASAP seminar that I will introduce the speaker first and then we'll start our talk today. Today's ASAP seminar will feature Lin Zheng, an expansional speaker from the University of Hong Kong. Lin Zheng is a four-year CS PhD student at the University of Hong Kong, Hong Kong, advised by Lin Pengguo. His research focuses on efficient and flexible sequence modeling, especially including areas such as byte-level language models, diffusion-based text generation, and efficient attention mechanisms. Today, he will talk about EvaByte, efficient byte-level language model at scales.
Yeah, sure. Thank you very much for the gentle introduction, Xinyu, and for having me here to discuss more in depth of our recent work, EvaByte. Please shoot me any questions if you have any at any time. Yeah, so let's get started. So this project aims to develop, this project, the EvaByte, trying to scale up the byte language model at scale and investigate scaling behaviors, how byte models without any tokenization behave, especially at larger scales. Yeah, so this is a collaboration project between University of Hong Kong, especially the Natural Language Processing Group and the Seminova Systems, where I work during an internship. Yeah, so the final model, the most interesting part of EvaByte, the finally delivered model is about its data efficiency gains, where we surprisingly found EvaByte, the final delivered models, EvaByte 6.5 billion, performs very competitively compared to like tokenized based language models, even with much less data, usually like 5x or even 10x less data compared to recent like open recipe language model, tokenizer based language models. So this is the most intriguing part we found during our development of byte models, especially at scale. Yeah, so let's move back to the very motivation. So the very motivation of this work is to avoid tokenization in the first place from the current like language model stack. So this is because like tokenizers are usually like externally trained from some small seeding corpus, and after being externally built, it just remains frozen or some just get detached from training. So especially from language model training. So this mixed model not fully end-to-end, especially because of the input sequences have to go through this particularly frozen tokenization process and then fed into the general transformer training. So this mixed model, so there are some bad properties for this setup, especially mixed model more fragile. So there leads to very subtle issues like glitch tokens, prompt boundary issues, etc. So for example, if you try to include some very under-trained tokens during the training progress into the prompt at inference time, then the model here the Queen 2.5 just output nonsense and just leads to very weird behavior, the generation behaviors. So this is mostly because the token, the whole token highlighted in yellow here is very rarely trained during the pre-training progress. As such, the model just cannot recognize such token, just terminate early. So we aim to address of these issues, and the very simple workaround of this to address of the challenges to use it's very naive. It just like operates on raw bytes, but without any tokenization, byte sequence is much longer than their tokenized counterparts. So this creates another challenge. So we have to pay much more like compute to like alleviate this tokenization curves. Yeah, so for example, in our in our data mix, which are mostly natural language text, math, and code, byte sequences are usually like 4x longer in than their like tokenized counterparts. And in other domains like images, audio, or video, etc., they're usually like 60x longer, or even 100 longer. So this definitely is a big problem and adds much more overheads during training to both training and inference. Because in standard transformer architecture, where the standard attention maximum scale quadratically with the sequence length, the much longer sequence just as much more compute overheads to training and pre-fitting procedures. And for inference time and for like decoding time, because of the autographic sequential prediction nature, the model has to pay much more time, have to spend much more like decoding runtime to generate the whole sequence in terms of bytes rather than tokens. Yeah, so we aim to address these challenges first, and our key idea is just to alleviate these issues with a more like streamlined, more efficient architecture. So this architecture like involves two components that we introduced to the existing transformer architecture. So the first one is about a multi-byte prediction module built upon the transformer backbone, and the other one is to replace the standard attention maximums with a more efficient alternative called EVA. Yeah, so this is a high-level sketch of our approach, and we now like dive into the details of each component. So the first component is called the multi-byte prediction. So the idea is pretty simple. It has been proposed in recent literature. So instead of trying to predict the right next token, multi-byte prediction module tries to compute, actually predict the next several bytes simultaneously. So this corresponds to like calculating the cross entropy functions from every like prediction head and aggregate them together, which serve as a final loss objective. So, but thanks to our particularly small Byte-level vocabulary size, which only like 300, this setup almost as no overhead to training with our like 8 different prediction heads. But it enables great inference time speed up because we can use established techniques like self-speculative decoding, like Medusa, some block-wise decoding techniques to speed up the decoding runtime. So the basic idea is just to use the first head as the verifier and the remaining ones as the drafters to propose new like byte candidates. And when you like after the first has verified of the proposed candidates, the model can output multiple bytes as one decoding step. Yeah, so this works pretty effectively and speed up the whole generation runtime greatly. Yeah, so we just use this very simple setting with uniform weighting of different prediction heads to perform the overall training process. But we also tried other decaying, some other like weighting schemes like powering decay to put much less data, much less weights to like more distant prediction heads. But we do not observe very like meaningful improvements to the uniform one. So we just stick it to the simple setup, use the uniform weights of different prediction heads. We just found them learn pretty well. Yeah, so this is the methodology of multi-byte prediction module. And we also do some probing, like kind of probing experiments to examine whether different prediction heads are learned effectively. So this setup is very simple. So we just examine the downstream test performance, which are mostly like choice tests. But instead, we're using the next token prediction log likelihood to discriminate this different choice. We use log likelihood returned by different prediction heads to select the choice which highest the log likelihood. Yeah. So and after plotting of this the performance of these different prediction heads, we basically what we found is, so basically, all of these different prediction heads have a very stable performance. So even though they are very different, they're very distant to the current position, like the 8th prediction head, which recurs to the 8th next, sorry. So the 8th prediction head would need to predict the 8th next bet. It still predicts very accurately compared to the first one. So the performance across different prediction heads just remain very stable. So this just indicates different prediction heads are learn very effectively, or they just leverage their learning semantics to do the downstream tasks. Yeah, so that's about the mini like toy scale probing experiments for different prediction heads. So this verifies our the effectiveness of our prediction multi-byte prediction module. Yeah, so however, and very unfortunately, with the multi-byte prediction alone, it is not enough to like speed up the whole byte models, because as the byte stream is much longer, as the byte stream quickly like fills up the entire context window, the standard attention maximum just becomes the main bottleneck. It's just globally, just greatly slow down the byte model generation. So we aim to address this issue, and we propose a very simple change to the existing architectures by replacing the standard attention maximum, which is a more efficient one, which we call EVA. So EVA is actually proposed in our earlier work in Aclear 2023. So it's based on a very simple variant of linearized attention or linear attention, which is a more common name in the literature. Yeah, so I believe most folks here are experts in this field, so I will only give a very high-level picture of how linearized attention works. So basically, the key idea of linearized attention is to like approximate the exponential dot product used in attention maximum with the dot product of two feature functions. So the feature functions phi here can be taken in various formulations, which we will be covering later. But the key idea is by plugging such approximation, we can enable a much faster calculation of the attention maximum. So this is basically due to the swap order of matrix multiplication. So instead of so in the case of standard attention maximum, where we first calculate the matrix multiplication between Q and key followed by V, we now calculate the whole multiplication by first multiplying key and V followed by Q. So in this sense, of this matrix multiplication happening in linear time, so the resulting algorithm just still runs in linear time with respect to the sequence length. So this is the key idea of linear attention and how it can kind of save the computation complexity. Yeah, so yeah, but the key idea, but to develop EVA, our key idea is to capitalize on the following observation, which is so typically linearized attention. So most linearized attention choose to compress the whole key value pairs information into a single giant global memory state, which could be 2D or even 1D in RNNs. But almost all of them trying to compress them into a single global memory unit. So the key idea of EVA is just to kind of distribute the whole global memory into multiple memory slots. So this is key idea and the key principle of like dividing and conquering. So the formulation here is pretty like straightforward. So we've still started with the standard attention maximum, but here the very first step here is to chunk the whole sequence, especially the whole key value sequences, into multiple disjoint groups. Yeah, so you can see that global summation over the entire sequence has been decomposed into two summations, and the inner loop tries to sum over all the kind of elements within each chunk, and the outer loop tries to iterate over all different groups. Yeah, so this is the very first step of chunking, and after that, we leverage another trick called multiply by one. So this kind of corresponds to multiplying the identity quantity and doing some rearranging in a cross manner. And after all that, so yeah, so we basically arrive a new yes, still equivalent formulation of standard attention mechanisms, but now we're operating on the chunk level. So you can imagine that on the term in right-hand side, we basically calculated the many attention mechanism per chunk. So we just sum over the possible elements within each chunk, and then aggregate by the chunk level attention scores as indicated in the term in left-hand side. So this kind of works like trying to calculate the attention mechanism between every query vector against the chunk summation, the chunk summary of keys and value vectors. Yeah, so at the in the third line, it still remains equivalent to the standard attention mechanism, and the very last step is where our approximation comes into play. So we just introduce two new approximations into these two individual terms. So for the right-hand side term, we still use the ordinary linearized attention approximation by introducing some feature function phi and trying to approximate them with linear time computation. But for the first term, we introduce a new function approximation called psi, which we will be describing in detail later. Yeah, so this is a key idea of Eva trying to distribute the global memory into local ones as trying to divide the concurrent in the chunk level. So this is a key idea. Yeah.
I have a quick question.
Mm-hmm.
So the capital C is the number of trunk, right?
Yeah, yeah.
So when the sequence length becomes larger, C will also become larger, right? Because you are fixing the trunk size.
Yes. Yes, exactly.
And I was also wondering, in this EVA linear attention, do you need to so the total number of hidden state is so you need to maintain C number of hidden states for each trunk, or you only need to maintain a single hidden state?
Oh, so you're referring to so we kind of maintaining several giant hidden state, right?
So for each trunk, you are maintaining a single state, and then for each trunk you have a state, and if there are a C number of trunk, you have C number of hidden states.
Yes, but not exactly. We will be covering how we reduce the hidden states for each inside each chunk. So the total capacity still remains very low, I guess.
Okay.
Yeah, so I will be covering this in the right next slides, I guess.
Okay, thank you. Please go ahead.
Yeah, sure. But before describing all the details, I would like to highlight some high-level intuition of Eva. So basically, Eva tries to interpolate between standard attention and linear attention. So instead of trying to store every single element into the memory slots, as done in standard attention, or storing every possible information into a global memory state as done in linear attention, Eva tries to find the middle of these two approaches and trying to interpolate them to find the nice sweet spot. Yeah, so this is high-level intuition of Eva. And another remark or some implication of Eva is kind of expands the design space of typical linearized attention mechanism, because instead of trying to improve the global memory state, trying to improving the coverage or some better organization of memory slots, it's much easier to improve that locally. So this is also the principle of dividing and concurring. So where some principles, criteria are much easier to improve than globally. Easier to improve locally than globally, sorry, yeah. So in this sense, it's completely complementary to ongoing research in better, in how to find, how to organize the global memory to be better, which better updated rules or which better forgetting techniques. Yeah, so this line of research includes the gated variant of random feature attention, the gated linear attention, gated delta net, test time training layers, Tetans, and HGI series, RWKV series, and Mamba series, etc., including many other works. Yeah, so we feel our work is complementary to this line of research. So this is the implementation we would like to highlight before diving deep into the details of the formulation. So so the most critical strategy here, so the most critical component here for EVA is perhaps it's just the chunking strategy. So we just use a very simple and heuristic hybrid design. So it's kind of like for each query position, we basically maintain two different types of groups. Like for the most recent neighborhoods, we define them to be singletons that only contain exactly one element. So it's kind of doing like exact attention or some local attention maxims. And for more distant ones, we define them to be fixed set chunks. Yeah, so they can be considered as I feel this can be understood as very simple combination of multiple localized linear attention maxims plus some block-wise local sparse attention maxims. Yeah, so as a result, this has drawing very interesting connections to previous works that's trying to like combine low rank and sparse some linearized attention together, like the scatterbrain, infinite, or more recent works like infinite attention, a la Kites and Lice and DeepSeek in essay paper, etc. Yeah, so I guess this hybrid, and in practice, we found this hybrid design strategy works pretty well. So we just use that afterward. Yes, so this is about the first component, how we define the chunking strategy, and the other component is the newly introduced one, which is about trying to approximate the calculation of attention scores. Yeah, so the precise function here, if we calculate it in precise terms, it basically calculates the attention score or the exponential dot product within each chunk. Yeah, so this is the most naive way to calculate this, but if we choose this way, it just returns exact quantities, but it's not very economic because we just bring back the quadratic capacity to the model itself. So it just becomes very expensive. And the other option here we explore it is referred to as like doubly linearized attention or some double linearization. So we just introduce a new set of random features or some feature functions by tilde and trying to approximate that quantity as well. So now, it's called double linearization because we now maintain two different sets of feature functions, phi and phi tilde. So the first feature functions is used to approximate the term in right-hand side, and the second random feature function phi tilde is used to approximate the first term. Yeah, so this looks very promising because both terms can be calculated very efficiently, but very unfortunately. So remember, our original purpose of EVA is trying to interpolate between linearized and standard attention maxims. But if you examine the edge cases, especially when C equals 1, so in this case, there is only one group over the entire sequence. So this just you can basically derive that it's reduced to vanilla linearized attention with random feature phi. And on the other hand, we try to examine the case where like C equals capital M. So that is every group only contains exactly one element, just like standard attention maxims. In this case, ideally, we hope that to approach the capability of standard attention maxims, but again, it just reduced the vanilla linearized attention maxims, which another set random feature function phi tilde. So it's kind of weird. It just gets us nowhere closer to standard attention maxims. We are still playing with like some mixture of linear attention maxims, which clearly not we want. So the third option, which we use in our experiments, especially is also proposed like in original work in EVA, is based on very simple heuristic. So instead of trying to calculate some like kind of feature function approximations, it just calculates the exponential dot product. But instead of trying to summing over all the possible exponential dot products, is try to calculate the dot product between the query vector against the weighted average of key vectors inside of that chunk. Yeah, so this kind of calculating the chunk level it's kind of calculating the chunk level key summaries and trying to calculate the dot product between the query and the chunk like representative features. Yeah, so it's still very efficient because you can pre-calculate the key summaries first and then use them for all queries. And it's also, and we also show that it's achieved perfect interpolation in the sense that when C equals 1, it just reduced to simple linearized tension maximum. But when C equals to M, it just gets equivalent to exact attention maximums. So in this sense, we just approach the standard tension better and better when we trying to allocate more and more groups in the formation of EVA. So it's kind of effectively interpolates between two attention maximums. So, and in practice, we also found this works much better than the above option. So we just use as by default. Yeah, so this is about the second component. And the right next token is then the right next component here is what like Sonin mentioned earlier. So this is our choice of how we can define the memory slots for each chunk. Yeah, so this involves the random feature function, and the formulation here, we just choose them to be identical to the one proposed in performer, which is a simple exponential function with randomly drawing Gaussian samples. Yeah, but what's different here is in practice, we found the model. So typically the random feature function phi here is defined to be very high dimensionality so that it can store much more information for each memory slot. But given that we have actually distributed the whole memory slot into multiple ones, it's possible to reduce the dimensionality to be very, very small. So actually, we also show in practice we show that we found this. What we found is even with scalar features, like let's say we only let the output function of random feature function y phi to be scalar, it still works pretty well. And in this case, actually, it has very interesting implication that it leads to a very degenerated form. So basically, you can so when the phi function outputs a scalar value, all the information from queries can be canceled out because it just becomes a scalar. And in this case, the memory slots just reduced to a simple weighted average of all value vectors. Yeah, so this becomes very interesting because now you can just store the entire memory slot with a vector, with the vector with the same dimensionality of value vectors. So this just becomes a very kind of very cheap storage. Yeah, so I hope this could address the questions raised earlier.
Why can you cancel out the phi QN term?
Yeah, because the phi outputs a scalar function, scalar value, so and it appears in both sides. Yep.
So you are using a like a future map that map d-dimensional to one-dimensional.
Yeah, exactly.
Okay, interesting.
Yeah. So
you observe very similar performance when using like S much larger than 1.
Yeah, exactly. It kind of performs much better, I would say, but it's not. Sorry, it's not much better, but it at least very close to very high dimensional feature functions.
I see. So I imagine like for each position you have a scalar phi km as the like the weight term, and then you do like weighted sum of the value vector. Okay. Okay, interesting. But I remember that like in the performer, and I think the future map dimension is very crucial for the approximation. I think in the original performer paper, they showcase that and the approximation error directly related to the future map dimension. Yeah, like to achieve very low approximation error, you need like exponential large future map dimension. But in this case, you only need like future dimension 1. Do you think this is counterintuitive, or do you have like more intuitive explanation for it?
Yeah, we've thought very hard about this very counterintuitive behavior, but we guess the most possible reason or the most probable reason is that we have already like distributed the global memory into multiple memory slots. So the number of memory slots can address or counter the effect of reducing the dimensionality of memory slots. So we kind of doing some transposing, doing some transpose over the memory slots from very giant but very short, but very few like number of memory slots to very long or a large number of memory slots, but with very small memory source or the memory capability. So I guess we are, I guess the most probable reason is just we are just trying to scatter or store information and scatter them across every possible memory slot instead of relying on one giant memory slot. So this kind of counter the effect of reducing the hidden set or the feature map sets.
Okay, I see. So let me rephrase the process of EVA to you can correct me if I'm wrong. So basically you have this like scalar valued future map, and then it like so this term would like comprise the entire trunk into a single value vector, and the phi k is like the weighted sum, and for each trunk you maintain a vector as some sort of trunk level representation, and in the end, so also for each trunk you also have a like a hidden state for later. So you need to calculate what is the importance score for each trunk, and am I understand correctly?
Yeah, totally correct. Excellent.
Okay.
Could I actually ask, what is the chunk size typically in this situation?
Oh,
about 8?
Yes. In our setup, so in our setup, we usually like use fixed chunk sets with 16 per chunk. So it's kind of compressing 16 like contiguous elements into one one vector with the same size.
I see. So did you guys try it with much larger chunk sizes? Because I would imagine that maybe the reason Songlin is pointing out is that it works well at a small chunk size because there's not a lot of
exactly. A good point. We actually tried a lot of options by varying like chunk size, but we found that up to like 128, the model still performs decent well. But after some hard threshold like 256 or some 512, the model just performs like good, just very slowly worse and worse. So we're just trying to when we're trying to do this hyperparameter sweep, we just end up with a very small chunk size like 16 or 32. Yeah, so we found this to be optimal in different setting across different setting, I guess, especially scale experiments. Yeah.
Cool. Did you try the performer style phi with a larger chunk size, or did you only try small chunk size with them?
Oh, in our hyperparameter sweep, we try both options, like trying to fix the chunk size, trying to search the number of feature maps. The output dimensionalities, and fix the output number of dimensionalities. We've searched the chunk size, but we found just as always, it's kind of counterintuitive that when you trying to increase the number of dimensionalities, it cannot address all of the kind of information lost by introducing a much larger chunk size. So it's kind of so let me rephrase. So we found it's not as effective to increase the number of dimensionalities. Yeah, so let's say we have a very high dimensionality feature map as let's say 64 or even 128. It even performs much worse than than say scalar functions with much smaller chunk size. Yeah, so we found it's much more effective to decrease the chunk size instead of trying to increase the number of dimensionalities.
Okay, thank you.
Yeah, sure.
Yeah,
Thank
so EVA is more like native sparse attention or MOBA than the traditional linear attention, right?
We tried Mamba, but our experiments at like our preliminary experiments were done quite early in the early development, like in 2024 spring. So at that time there is no Mamba 2, and we found very limited state size.
Oh, I mean MOBA from Kimi AI.
Oh, MOBA. Oh, sorry. We didn't try that.
Because I found EVA is conceptually very similar to MOBA.
Oh, yeah.
MOBA
right.
also for each trunk they have a compressed vector and a compressed key. I think your model is like mostly very similar to like the compression branch of the native sparse attention, but you don't have the sparse attention part, right?
Yeah, we only use like simple local, like block-wise local attention maximums.
Oh, it's like you still have the local sliding or trunk attention?
Yeah, we do not use sliding windows. We just use like very sim-threaded local block-wise attention. So we just split the whole sequence into multiple like local blocks, and each local block moves as a sim-thread as a block size, and trying to do the local self-attention within each block.
I see. So block size is 16, right?
Block is much larger. In our experiments, we actually use like 2000, so you can you can think of it as the setup in infinite attention the setting.
I see. So you have a large local trunk attention, and for the distant token, you use like compressing strategy and to compress like each 16 token to one token. And it's like a kind of a weighted sum, and the weight is determined by the phi km, which is a scalar, and you do the normalization for the entire block.
Yes, exactly.
I see. Thank you for your explanation. I think I understand what you were doing.
Sorry. Yeah. Actually, we feel like after you combining up this component into the actual implementation is no different from a very simple like low rank plus sparse attention mechanism. So basically rely on so I guess the algorithm still mostly relied on the local information to be aggregated and to like retrieve the correct information, but it's also like preserve the all distant information without erasing any of them. So it kind of works like in that way, in that hybrid way. So I think it should be pretty straightforward, and not I would say should be nothing new to the field of like trying to combine local attention, sparse attention, and low rank attention and the linearized attention mechanism together. So I think should be pretty relevant to that line of research.
Yeah, so I was also wondering, like, personally, you say like the future map dimension doesn't matter at all. You can use dimension 1. I was wondering, what if you remove the local trunk attention? Because like I think local trunk attention is like doing the heavy lifting, and then the linear attention part only need to memorize some very distant token. And so the memorization burden is not that heavy for linear attention, and the trunk attention can handle it very well. So this might be the reason you don't need to have a very large feature dimension for the linear attention part that is purely responsible for outside the trunk's historical information.
Yeah, exactly. Very good point. So that was why during our hyperparameter sweep, we completely disabled the single attention maximum. Sorry, the local chunk attention maximum. So our experiments, especially the hyperparameter sweeps over the chunk size and number of dimensionalities, based on the very simple setting where the local chunk attention is completely disabled. So there's no local chunk attention, and all of them are just fixed size chunks. And
so you are indicating that even without local trunk attention, the future map, future dimension 1 is like sufficient.
Yeah. But in that case, yes.
I see. So do you attribute it to like because for each local block you have a vector? So in this sense, the total amount of like hidden state memory for this attention mechanism is like dynamic growing. You don't have a fixed size memory, and in this scenario, like you don't need like so future dimension 1, and then you are like basically you are compressing 16 token to 1 token, and when you keep increasing the future map dimension, you are compressing 16 to the size of S, right? And so first, it doesn't make sense for S larger than 16, and then it makes sense because like the memory size is like dynamic growing.
Yeah. I think the most I think your point is correct. It's totally correct. I think the main reason should be the dynamically increasing number of memory slots that account for most of the information, not like being erased from other like memory slots. So I think but this is also the reason why we do not call it the linear time attention maximum, because it's still like roughly quadratic in terms of sequence length. So we didn't mention the name of linear attention maximums or whatever. So yeah, we feel like it's still costly with extremely long sequence length, but with intermediate or some mediumly long sequences like 32K or even 1 million should be pretty good to go, because the constant factor of the quadratically many computation cost is very small. So I think but I think the reason for having a very small number of dimensionality should be a dynamically growing memory state.
Yeah, that makes sense. Thank you for your explanation.
Yeah. Yes, thank you very much for your insights. Yeah, I guess. Let's get back. So without this in mind, we can just implement the model in a very simple way and in a very straightforward manner. So because it's a chunked based model, and it works like a cross attention maximum between every query vector against every chunked keys and value like summaries. So you can basically implement in just in flash attention style. So you can just do the telling and starting over the entire sequence in the usual way flash attention does. Yeah, so here is some high-level sketch of the whole algorithm. So it's very simple. So we just pre-calculate of the chunk level outputs and catch them to some proper storage like HBM, and trying after calculating all these quantities in parallel, we just calculated the outputs for each query, where each query is also calculated in parallel. So just fetch the corresponding chunked output to the SRAM and try to calculate the whole quantity and output. Yeah, so this is the whole algorithm to implement the EVA, which should be pretty straightforward. Yeah, so and after that, the decoding scheme is also very, very similar to standard attention maxims, except so it also does very similar things like trying to maintain some KV cache and trying to calculate for each incoming query token or some token bats. It try to calculate the attention maximum between the current query bats against the elements inside the Kiwi cache, and calculate the outputs and trying to produce the next bat, and then put them back to the cache. Yeah, but what is different here is every time the model has consumed capital S bats, which is number of singleton groups or the local block, it's just popped up the most recent capital S bats from the Kiwi cache, and transform them into local memory slots in the same way we did for like localized linear attention, and then append these memory slots back to the Kiwi cache. Yeah, so this kind of shortened the Kiwi cache length. But in terms of, it works like doing the orthogonal way to of multi-latent attention. So instead of trying to reduce the hidden dimension size, we're trying to just reduce the sequence length. The Kiwi cache length. So this is what we refer to as compressive decoding. Yeah. So the algorithm in right-hand side provide some sketch of the whole decoding algorithm. So which is all very straightforward. Looks pretty similar to standard attention decoding schemes, except every time we consumed a fixed number of tokens, we have to invoke the transform function and shorten the Kiwi cache length. Yeah, so that's pretty much of the EVA attention maximum. And with all of these components combined, like replacing the tokenization with byte-level inputs, or we use some more efficient attention maxims instead of the standard attention maximum, and also some multi-byte prediction module on top of the transformer backbone just enables effective scaling. So our final experiment setup is like with 6.5 billion parameter counts and operating on like 32K contact lengths and training over like 1.5 trillion. 1.5 trillion bats, which correspond to 0.5 trillion tokens in our data mix. So this yields a very strong performance. And so it yields very fast decoding runtime. It enjoys very exciting data efficiency, and it removes most of the tokenization quirks and has some very native support to multi-model data types. Yeah, so we'll examine these details one by one. So, but before diving into the details of the results, here are some very detailed breakdown of pre-training data we use. So basically, we just use stages the pre-training. Oh, by the way, all of our pre-training training runs happen on SemNova systems particular hardware. So which is SN30 reconfigurable data flow unit. So yeah, and then the pre-training splits into 3 different stages. So first stage goes through like 700 billion bats and with some proper linear decay. And in this phase, we mostly use like FunWeb EDU, DOMA, and StatV2 for coding corpus. And for the phase 2, the most critical change is we swapped out the data mixture from like FunWeb EDU and swapping the data from like DCM, because we found it yield very much better performance actually. Yeah, we also added some attending portion of instruction data for us to better monitor how bat models performed in downstream tasks. Yeah, and in the last phase, we do some like it should be called like mid training stage, where we perform different independent annealing runs and try to merge them with model soups by just averaging the model parameter by parameters. Yeah, so these different 2 runs have varying amount of data and data mixtures, but yeah, we found increasing the amount of instruction data does not matter them a lot. So we just use a majority data source to be TCM. Yeah, so that's kind of the scheme for data mixtures. And we also record some instability, some kind of grid instabilities during our training runs. Especially the most interesting part or the interesting issue here is called what we dub as embedding collapse. So this one is very weird. So we just found some intermediate checkpoints that started to make very random and very weird typos. So here is an example in right-hand side. So basically the model, some intermediate checkpoints could follow the semantics to write the code very well, to write the whole piece of code, but just like transcribing or some copying of the variable name got it wrong. So it looks very weird because almost all the other stuff got it correct. Yeah, so we observed this weird embedding collapsing issue very frequently during the training, but fortunately, this issue just got self-resolved every time, like after 100, 200 training steps. And it's not did not appear near the end of the training phase, so we consider it as a more of a temporary issue. Yeah, so but it is very interesting, and we do not know why there is some just kind of embeddings collapsing into together. Yeah, so it should be some particular some bugs specific to the byte-level models. Yeah, because in token level models, the very weird combinations of these characters should not happen in the first place. Yeah, but anyway, we also found some other unstable issues like lost backs, but not very frequent. So but we also like made some hyperparameter changes, made flights along the way of pre-training. So most useful tips we found is, so we found lowering or decreasing the Adam optimizer's epsilon to much lower value really helped a lot and helped stabilize the training run and helped the speed up the training convergence. Yeah, and another technique we use very often is to skip batch whenever there's the back, and whenever there's back, we just give the batch we just give the several batches that leads to that last back, as try to roll back the checkpoint to the earlier state, which should be still healthy. Yeah, and the last technique we use, especially near the end of the training run, is we periodically like reset the optimizer state to remove like potentially bad noise, like historical estimates. Yeah, so this documents our efforts to address the instability issues. So here are some results to illustrate EVA's advantages. Sorry, EvaByte's advantages. Yeah, so the first about the speed up. So we found both our components, the multiple prediction, the efficient attention maximum EVA could speed up the byte models, and whichever one disabled, there is a scalable, there a great slowdown for byte modeling. Yeah, so and with these two components combined, they even leads to like 2x faster decoding runtime than tokenizer-based language models, which is very promising. Yeah, so, and it will also examine the overall performance, and this is where we observe there is a great like data efficiency, because if even train with like 0.5 trillion tokens equivalent, the model could perform quite competitively with recent like open recipe language models with open data like DCM, MapNew, OMO2, etc. And even with much less data, like 5x or even 10x less data than OMO2. Yeah, so this is still very interesting, and we trying to understand this aspect, and we have thought very hard about this reason. And one possible reason of our hypothesis is byte models, due to the much longer byte sequences, might bring much more like gradient descent steps under the same amount of data. So in this case, one may argue that the byte models might fit the distribution much better than tokenized models because of more gradient descent steps. Yeah, but that's only one hypothesis. Our hypothesis, and we leave a very systematic investigation for future work. Yeah, so that's about data efficiency. We also did a lot of evaluation studies to examine the components. And so, for example, in EVA, we just observed the model. The model with EVA achieved very same performance as standard attention mechanisms. Yeah, so this verifies the effectiveness of and the scalability of EVA, and despite it's a very limited scale, so it's only like 1 billion model with 100 billion bytes. Yeah, but anyway, we also found, but when comparing like byte models and tokenizer-based models, we found the byte model actually catch up with the tokenized model very quickly. We like catch up with the performance with much less data, like 3x data. Or when comparing them under the same amount of data, byte models perform much better. So this again validates our hypothesis of data efficiency. Yeah, so we also track some intermediate performance over the entire pre-training progress. So we found the downstream text performance just steadily improves without any sign of plateauing. So this clearly indicates the current performance of EvaByte has not saturated at all. And also, there's a lot of room for future improvements. Yeah, so oh yeah, so we also compared the intermediate checkpoints of EvaByte against other intermediate checkpoints released by other model series like OMO1 and OMO2, and when comparing them under the same amount of data, EvaByte also outperforms them consistently. So again, the data efficiency. Yeah, so we also tried some basic post-training at a very limited setting. So we found this byte model scale very well with fine-tuning and can do some basic instruction following tasks. And so of our post-training are very limited, and there is a lot of room for future exploration, especially on post-training recipes. Yeah, so okay, so this the other very interesting like snapshot of how byte models can address tokenization quirks. Yeah, so this problem is usually called the prompt boundary problems. So this roughly about like so during training, so usually we will do is concatenated both the prompt and the boundary together and tokenize the whole piece as a whole. Tokenize both the prompt and the completion as a whole. But at inference time, you are only given prompt, right? So there's no way for you to get the prompt with the completion. So you have to tokenize the prompt individually. And in this case, because there is a missing completion, there might be some incomplete tokens at the near the end of the prompt. As in this case, the basic tokenizer-based models cannot recognize these incomplete tokens. So, for example, in Queen 2.5, it will be trying to vary the prompts and boundaries. So they basically most of the times the Queen model just got it wrong because they just cannot recognize what is the piece of incomplete token is. But so for very weird combos of the prompt boundary, like a new line followed by 3 consecutive white spaces, the model can get it wrong, get it correct because every character is associated with a leading white space. Yeah, but in terms of best models of these different prompt boundaries leads to just converge to the same outputs because there is no notion of incomplete tokens. Every token or every byte is represented as individuals. So the model just looks very promising and robust against these changes. So this is about how models can fix tokenization quirks, but actually we found the model is not very robust, especially in tasks like character counting, string manipulation, etc. So what we found is byte model just performs as bad as typical tokenizer-based models. So here are some very concrete examples. So if you text the model to output the specific character or some order number in some particular string, the model just get it wrong. So our hypothesis here is like the counting problem or some string manipulations is likely not a problem of some superficial like textual pattern matching. It's more of a problem of some reasoning on some other representation issues or some other deeper roots. So because models in this way have to like dig deep into like semantic understanding to retrieve the correct information instead of trying fully relying on some superficial textual formulations, some textual like simple pattern matchings. Yeah, so we observe that model is not as robust as expected. Yeah, so that's kind of negative finding in our preliminary experiments. Yeah, so the last piece of results comes to our multi-model exploration, which is still ongoing and preliminary at the current scale, at the current stage. So this is due to actually attributed to the great consequence of bad models, because any like digital content, like different data types, audio, images, text, etc., can all of them can be represented as some particular bat stream. So just as we can represent the text as a stream of UTF-8 bats, we can just represent images as another kind of bat streams. Yeah, so the only problem remaining here is to choose a proper like encoding scheme to make the model efficiently and effectively calculate or some doing the repetition learning over these image bats. Yeah, so in our preliminary experiments, we choose JPEG, which is due to our limited context length, because we only have 32K and we cannot fit the whole like raw bats images like in PNG or big 64 format into the single context window. So, and with the choice of JPEG, which is a lossy compression algorithm, 64K pixel image usually takes like 10K bytes in terms of context length, which is acceptable. Yeah. So, but please note that the choice of JPEG here we made here is not very optimal because it's very lossy. It's actually the lossy compression algorithm and actually optimized for human perception instead of for machines. So it's probably not an optimal choice. Yeah, but anyway, we can just feed the interleaved images and the text pair bat streams into the like transformer model, the EvaByte model, and for vision language training. So this step involves that doesn't involve any architecture change. So this again validates our previous claim that bad models show very native support to like multi-model data types. Yeah, and after fine-tuning to 20K training steps, we found the model could vaguely generate complete the images given the left half or some upper half of the images, or given the complete images, the model could generate captions with great details. But so here are some examples in the right-hand side. But again, there are a lot of hallucinations happening there. So there's definitely a lot of room for improvements. Yeah, so I guess this pretty much of the results we delivered for EvaByte. And so here are some limitations of future works for EvaByte. So to summarize, our current tweaks to the transformer architecture includes in several aspects, so the first one is definitely about the input, where we just remove the tokenization in the first place with just make the model operate on bats. Yeah, so this makes the model a bit more flexible. And the other component we change is about the output, where we replace or upgrade the next token prediction to multi-byte prediction, which also kind of established techniques in recent literature. We also modified the attention maximum from the standard attention maximum to a more efficient one called EVA. But if you examine the components, if you examine like by comparing component by component, you basically find that the feed-forward networks, which is the most critical components in today's transformer architecture, just remains the same and untouched. Yeah, so, and especially after we optimize the whole attention maximum, it just becomes the majority. So it just takes the majority of the flops here. So it's very necessary, almost a must, to improve the feed-forward networks efficiency, especially in the context of bad models. So there are several ways to address that. So for example, if you view the feed-forward networks as a as a memory layer, or some cross-attention maximum between the input activations and the model weights. So you can just use acceleration techniques to attention and apply them to FFNs. Yeah, so you can also use other like modules to replace the FFN entirely, like sparse memory layers or some MOEs, etc. I guess most of them should be equally applicable. Yeah, so that's our current summary of current progress on the architecture research. And so the last piece of questions and future works includes the appropriate data representation. So given that the model could take any bit streams it was given, very interesting question here is, so like there are many valid choices to represent the same piece of data. So the question is how we can choose the best encoding scheme for the same piece of data to improve either the efficiency of learning or effectiveness. Yeah, so it's kind of, for example, you can use compressed bits like gzipped input streams to do the modeling, which should be probably more efficient, but it should be much less learnable because the gzip compression has compressed out most of the like statistical patterns that yeah, so that's about the data representation, especially in the bit streams. And on the other hand, we also aim to improve the overall architectures to the next step. So basically, for best models, what we expect is so it's kind of doing some transposing over the input activations. So in typical tokenized models, so basically you have a mediumly long sequence length with much higher dimensionality or some hidden size. But in terms of bad model, because of the very sparse information units inside very single individual element, you would expect a very long, extremely long sequence length, which very short dimensionality to account for the increased flops. Yeah, so in this case, we are moving from very dense computation to very distributed computations, where all the information of the representations are learned scattered to like kind of distributed over the entire very long bit sequence, and just all the information just scattered around the entire sequences. Yeah, so we hope this can like bring much more distributed learning representations here. And a final remark is we feel like bit sequences looks like a very suitable test bed for efficient like sequence model research, because there has a very naturally very long sequences, especially in images or visual other visual domains. Yeah, so we hope this could be a very interesting for future like efficient architecture research. Yeah, so that's pretty much of today's talk, and thank you very much for your time, and please shoot me any questions if there is any.
I had one question about the amount of data. You guys talk a lot in the paper about how efficient it is in terms of data. One thing that's not mentioned very much that I was curious about is about kind of the relative number of optimizer steps
Yeah.
You know, and like kind of number of tokens and how fast it runs to do the training relatively. Because even though you use less data, I got the sense that it still might take about the same amount of time of training.
Yeah, yes, exactly. So in terms of the same number of like kind of training steps, we do some toy scale evaluation studies. So in terms of the so we basically we calculate so we run two different models, one with tokenizers and one without, and we both of them trying to train them with the same context length and with same number of updates, because 100 billion tokens just corresponding to the same number of updates in 100 billion bytes. So in this case, we found the model and with the same data, of course. Yeah, but in this case, we found the model catch up with the performance in terms of token models, tokenizer based models, but not better. But when you're examining the same amount of data, in our case, the 35 billion tokens correspond to 100 billion bytes. In this case, the model just greatly outperforms the tokenizer based model. So I think this illustrates the effect of the number of updates and number of tokens or number of data should illustrate their relationship a bit. I'm not sure if that helps.
Yeah, that's great. Thank you. So to me, looking at this, then my understanding is that for about the same amount of training, EvaByte, it has lower scores, like less good scores, but that with less data, but more training, it improves beyond. Okay. Great. Thank you.
Yes, thank you. So we just allocate much more compute to each individual unit of data. So a very critical problem here is about the token efficiency, how we can use much more tokens with the same unit of compute. So which is kind of the reverse of data efficiency, where we can achieve much better performance with less data. So yeah, this should be a very interesting problem to explore. Yep. Any other questions?
We have several questions in the chat.
Oh.
Could you read the question and then answer it?
Yeah. So here is a question about how much sensitivity to number of bytes predicted ahead. In this, how much the number of addition has? Oh yeah, next question. So basically, in our multi-byte prediction module, sorry. Should be, oh, sorry, should be this one. Oh, this is actually a next question. So basically, the throughput with respect to the number of bytes, number of prediction heads is usually like measured with the acceptance rate during the self-speculative decoding step. So basically, we found is if we are allocating, so let's say if we are allocating like 8 different heads, so the average acceptance rate is above 7. So it's great. So it's a very, it's kind of a very counterintuitive acceptance rate, because you cannot achieve that much. But in terms of bets, we found many like repetitive patterns. So it's kind of linearly increasing with the number of bets. Number of prediction heads. Yeah, so I hope this could address this question. Yeah, but anyway, the other very interesting pattern phenomenon we found here is the acceptance rate is very large. It's very, very high than expected. Yeah, and another question is about how are the multi-model data types are supported, like images. So I believe this should be well addressed in the right next. Just in this slide, so we can use so basically any different encodings of images like PNG, base64, JPEG, and other like formats are well supported. So it's only a matter of the only thing that matters is how the different encoding schemes affected the efficiency of the implementation or the effectiveness of learning or the learnability. So how if we try to compress the image too much, the most of the structures like statistical patterns will be removed due to the entropy coding. So in this case, the model could not learn very useful semantics from the encoded images. So there is almost a trade-off between the efficiency or the compression rate and the learnability, which is a active topic and a problem in terms of bad models, which I believe there is very few work on that aspect. Yeah. So I hope this addresses this question.
I have a
yes.
So why do you have a 32K context length limit?
So this mostly due to our compute budget. So we only have like 200. So we cannot have 200 A100 equivalent because we are training on own hardware. So we can definitely support much longer contact length, but it's a bit more difficult to implement, especially the context parallel and the context budget is just not allowing us to increase the contact length.
I see. So this is the maximum sequence length that you can support without context parallelism.
Yeah, kind of so.
I see.
Mm-hmm. Yeah, so it works like a very hard limit because many like different data types like audio and videos, we cannot fit the raw bits into the single context. So that's also why we choose some lossy compression algorithms to do that. Oh yeah. So the question here is, do you use positional encoding? The answer is yes. We just use rope just right before the attention. Sorry. So we also use positional encodings. So the attention encoding just happened before after the projection of keys of value matrices and before the actual forward pass of EVA. Yeah, so you can basically think of that as performing regular rope.
Do you think it makes more sense when you apply rope after the compressing?
Oh yeah, that's a very intriguing question that has triggered me. Has triggered a lot of very especially on positional interpolation issues. We found that after we did a few application study to study the order or the position where we inserted the rope, and our initial results are that just remaining the original ordering, like just right after the key value projection and before the EVA forwarding, gives the best position interpolation capability. And otherwise, other positions like after the compression step or apply double rope over both the compression, both the chunks and both the local attentions, does not yield very meaningful improvements. So we just end up using this very simple and very original implementation. Just use the right after key value projection and before the EVA forwarding.
I see. So for the right-hand side of the equation, you have 5 km. So you apply the rope before this future map.
Yeah. Yes.
But I think like this kind of like you are losing the relative position encoding property of rope. Yeah, if
Yes.
if this way. Yeah, but like might you yeah, like sort of like treating rope as absolute position encoding.
Yes. Oh, that's a very interesting viewpoint. Yeah, but makes sense. So it's so it is why we expect much better positional interpolation capabilities inside. Oh, it's interesting.
Yeah, because if you want to maintain the relative position encoding property, you need to apply the robe after the future map to map as of
Yeah.
knowledge.
Yeah. Yes. Yes. But we yes, in this very makes a lot of sense.
Oh, I also have several questions. So regarding the computational challenge, you mentioned like the FFN layers still being a bottleneck. So have you ever tried like reducing the model dimension? Because like the vocabulary size is much smaller, and you probably don't need that larger model dimension to encode this byte-level data.
Yes.
Have you tried that?
We tried some very crude approximation. So our approach just mostly follow the memory layer view of the FFNs. So we just viewed it as the cross attention maximum between the input activation as queries and the model weights. The first layer weights as keys, and the second layer FFN linear layers weights as values. So in this case, we just apply some linear attention, very crude linear attention approximation to that. So that, of course, this results in very low efficiency because the gem structure is completely destroyed. But we observe very like degraded performance overall in terms of downstream tasks. So we did not explore further, but I guess there are definitely room to improve that because we were only using a very crude approximation, just vanilla. It's kind of vanilla performer to the cross attention maximum view of FFNs.
I see. I also have an idea like, can you apply FFN on the compressed vector? So you can like basically you can reduce the FFN computation by 16 times.
Interesting. So basically means after calculating of these compressed or some chunked compressed inputs, we just feed them into the upper FFN layer and trying to.
And you can rely on the residual collection to distinguish between different byte token representation. But you can share the FFN representation, and so in this sense, it could like reduce the FFN computation cost.
Yeah, you can use much shorter sequence for the FFN layer. Yes, this makes a lot of sense. I guess this should be doable. Yeah, actually, after aggregating like 16 elements into one vector, doing the FFN layer should be making more sense because unit information from every individual byte embedding should be much sparser, much sparse. Yeah, should be. Yeah, this very interesting. I guess it should work. I guess so. But I guess I'm afraid there should be a lot of architecture changes should be made here because you basically you have two different streams. So the one is about different queries. Oh, it works like perceiver, I guess. So you made different streams, one for queries to do the EVA attention, and the other stream to process the compressed inputs and trying to pass them through FFN layers. But I guess this should be a very interesting design.
Yeah, I think maybe the main difference is that maybe you will try to maybe compress and uncompress for each layer. So maybe you can also use EVA for the before the MLP. Yeah, again.
Yeah. Yes, exactly. Oh.
Yeah, and maybe I have a question about maybe the multi-token prediction because yeah, in comparison with the better transformers, I think that the encoding cost is maybe increased due to the MLP because you will always compress and uncompress. But it seems that the decoding cost can be reduced, or maybe just can be doing parallelism, because that even with one single hidden state and use maybe different heads, I think because I do not see many tokenized large language models, they actually use multi-token prediction for the inference. Yeah, so I'm thinking about as maybe this maybe illustrates that maybe decoding may be much easier than encoding, because that for encoding you always need MLP to be operated on the raw information, but decoding that you only need one hidden state, and they can use a very small lightweight heads to extract maybe the next 4 or maybe 8 eight tokens. Yeah. Maybe,
Yeah. Yes, makes sense. It should be much easier in the decoding phase than actual decoding and actually encoding procedure.
Regarding the multi-token prediction branch, have you ever tried some more sophisticated method like those using like DeepSeek V3? They have a multi-token prediction. I think they have a very lightweight autoregressive mechanism with this like a multi-token prediction. Yeah, I think they like do a autoregressive decoding for the last layer.
Yeah. So they also like do some pseudo teacher forcing for the subsequent prediction head.
Yeah, have you ever tried that method, or you found okay the simplest method works equivalently well?
Yeah, so we did a lot. We did a few ablations over the different designs of the prediction model, the different prediction heads, but mostly on the weighting side. So we just tried different weighting, power decay weighting, and some other weighting schemes, but found the uniform weighting scheme just works the best. So we just use that, and we just stopped exploring other aspects like how we can further improve the multi-byte prediction module, like the one used in DeepSeek paper, DeepSeek V3, but we did not explore that. We found the model performs already quite well, so we just ended up at that.
I see. Thank you.
Well, in the current case, that during generation, you can see that for different heads, they actually can generate maybe consistent information. Yeah. Do you see some case that because that I think one concerning is that because that they are generated separately, one concerning is maybe some junk token or it's missing something. Yeah, they think others will generate it.
Yeah, so but our main setting initially we tried just trying to predict red 8 best simultaneously without any verification, but we found there are a lot of there is indeed very high degree of repetitions. Many different prediction has just output very just the same characters, so just kind of repeat the first character 8 times. Yeah, so we end up using some other speculative decoding techniques like Medusa. So we just using some tree decoding and verification schemes so that we could ensure such repetitive patterns will not will never appear after the verification phase.
Yeah. I think this might be a problem of a parallel prediction for all those tokens.
Yeah, that's right.
And if you use like DeepSeek V3 multi-token autoregressive strategy, this might be elevated.
Yeah, because I think if you only use one layer to do the autoregressive decoding, it is still cheap. Yeah.
Yeah, because it's like enhance the consistency, avoid repeat.
Yeah.
Yes, indeed. Yes, I think it should be pretty exciting and actually very efficient to use a very lightweight decoder to perform the actual decoding phase.
You have inference efficiency comparison with those tokenized model?
It should be right here. Yeah, but we do not observe, we do not plot the measures of batch inference scenarios because it is way more difficult for us to implement a very complicated serving-based inference.
I see.
Yeah, so this mostly measures with like just native single batch Hugging Face generate. So there are a lot of overhead over them. So, but there is also very high degree of overhead in Byte models. So I guess should be some like kind of app comparison. Yeah, but roughly tokenized models is kind of 2x slower than Byte models. Than EvaByte.
So both the baseline model and so does the baseline model use multi-token prediction or just?
Oh no, I just use standard standard decoding procedure like sequential token by token and left to right.
Without speculative decoding?
Yeah, without any speculative decoding procedures.
So do you think like the inference time improvement comes from like speculative decoding?
Yeah, I guess so. I guess majority of the speed up should be coming from the multi-byte prediction or speculative decoding components. Yeah, but this is just initially speed up. But when the model just keeps generating, and the byte stream filled up the whole context length, the model without the efficient mechanism just becomes much slower to decode. So we also have to rely on efficient detection mechanisms when there is a very long context length, or we have a very long prompt. So
I see. So you are reducing like 4 times the KV cache size because like 1 token equals to 4 bytes, and you have like 16 times like compression ratio, and overall KV cache is like reduced by 4 times. Yeah, makes sense because yeah, makes sense.
Yeah, but in the plots showing in the right hand side, we both the x-axis and the y-axis are measured in bytes. So it's kind of like measuring apple to apple because the byte model is really consuming a lot of context length, especially during inference time. So produce very just leaves very high, very large, very like yeah, I guess very high computation costs in decoding time.
Do you have some non-context evaluation?
You mean the ruler?
Oh, yeah, maybe some like needle in haystack or.
Yeah, we did. We examined that as a middle during as some intermediate checkpoint, and we found our ruler tasks just performed just very same as the standard transformer, sorry, a similar trained transformer. So we do not explore further on that benchmarks. So
very similar performance.
Yeah. So I think it should be primarily some like needle in a haystack. There are single query and multi query and some commonly words and other benchmarks. I like most of the ruler benchmark. EvaByte performs very similarly to transformer. So I guess we do not explore that further, and we think that there's no problem for that to retrieve correct information from the context. So we just leave that as take them as for granted. So.
Okay, so you don't think like this compressing stage will hinder the perfect retrieval performance?
Okay. Yeah, we did. We were afraid of this compression capability that might hinder the retrieving information, the capability of retrieving information. But after examining the benchmark accuracy, benchmark performance of ruler, we felt a bit confident, so we just move on and without evaluating them extensively.
Yeah, I'd be very interested in seeing those non-context evaluation benchmark because like the current benchmark results are all from very short context, like MMLU and other LM harmless benchmark. Because you previously mentioned you have a relatively large local trunk attention. So if the evaluated sequence length is small, it like reduced to the global attention, and yeah, it remains to see how the the outside of the trunk attention part help for very long context scenario. And this is the part I'm very interested in.
Yeah, yes. But for like MLU or HumanEval and other tasks, although we use the like local chunk attention with 200 bytes, it's still translates to like 500 tokens, where some some evaluation instances also surpass that token length, like usually 100 number, usually like 700 or 800 tokens. So it's also crossed the boundary of local chunk attention. So at least
what's your trunk attention size again? I remember it was 2K.
It's 2000. It's 2K. It is 2K bytes. So which amounts to like 500 tokens.
I see.
In the actual sense. So it's not very. It should be pretty large, but not very large to include all the evaluation instances into account. So I guess some of them still have to access the remote chunked compressed compressed output.
Yeah, thank you for your explanation. Does anyone have further questions? Okay, seeing that we don't have any further question, and let's stop here. And thank you very much for presenting.
Yes, thank you very much for the talk.
Yeah, thank you very much. Thank you very much for hosting.
Bye. Good night.
Yeah, indeed. Thank you.